Good morning, everyone. Sorry for making you wait. We do these polls for to make us improve our next few webinars. That is the reason we do the polls. And I would like to welcome our speaker, Ms. Nutan Agarwal, who has been a semiconductor professional for last 27 years, and she has worked for companies like ARM, Synopsys, Masab Electronics, and she has spent 15 years in STMicroelectronics, and she has worked as a from she started working as a section manager in memory design, and then went till becoming a director of engineering operations in the ARM. So it's an extensive research, and she has great leadership qualities along with expertise in memory design, test, CMOS, EDA, circuit design, and program. And she is also educated from Kanpur. And I think now I would like to hand over the session to Miss Nutan, and she can take it on from there.
Yeah. So thank you, Adarsh, for the introduction. So, yeah, I think you covered it all. So, hello and welcome to everyone who has joined. I will just try to share my, presentation. Okay. So once again, hello everyone. Good morning. So, without spending any more time on introduction and all, I think that has been covered. So, I'll just start. Okay. So, as Adarsh said, this webinar is for memory architecture and SRAM cell design. We will be talking in general memory architecture, but we will be focusing more on specifically on SRAM architecture and SRAM bit cell design. So, it's a very big topic in itself. uh, I think everybody should understand that it's not something which can be covered in a 1.5 hours webinar. So I'll try to talk about some important aspects, but not a lot of detail of everything. But overall, I will try to cover the architecture part and the specifically the bit cell part. Uh, so there's a lot of material available on internet on all these things since long. So for pictures and all, I have referred to that. But a lot of my experience is on memory design since ST, Synopsys, and ARM. So all my learnings are from that industry experience, which I'll try to share some of that with you today. So I think all those who have joined today, everyone knows what is a memory. But just to give an analogy here to begin with, we all know that we have memories inside human brain, and how critical, how important it is for our own functionality. We can't live without our memory, all right? But the sad part is that in spite of all the medical advancements, if something, God forbid, goes wrong with our memory, it's very difficult for to repair, to understand what's going on. Thanks to semiconductor technology, we have memory in every gadget we use, from phone to computer to our cars, whatnot, right? Uh, Cameras, and thanks to the technology, yes, this part of memory, which is man-made, is understandable and fixable to a large extent. So this was just to make an analogy between the human brain and semiconductor memory. So moving ahead, I will just try to put in context one of the typical uses of memory. We know memory is used in all different ways and at many, many places. But in a computer system, how this memory is arranged, because a computer, we know, lots needs lots and lots of memory, right? We are storing lots and lots of applications, lots and lots of data instructions there. So, what is the purpose of this memory capacity and memory hierarchy? Why do we maintain that in a computer system? So, what happens is that the most used data, most used instructions, okay, needs to be stored somewhere on the very close to the close to the processor. So, those are typically the fastest memories, and typically the SRAMs. and SRAMs converted into cache memories, basically to make them even more fast. They could be costlier, but they are fastest in speed and they are kept very close. And since they are used for most frequent data and instructions, they are used in small size basically. But here, whatever small, big I use, these are you can say kind of relative terminology. Every application is different. Every usage is different. So these days, the fastest SRAMs in 3 nanometer, 2 nanometer technologies are reaching up to 4 gigahertz performance also, which is what I have mentioned here, 250 picoseconds. And then in the computer system, uh, when the for the storage of less used data, less used instructions, we use technology like DRAM memory technology, which could be cheaper, maybe slower, but it serves the purpose because we are not storing the most used data here. We are storing less used data instructions here. Then we have things like operating system itself and lots of applications to be stored. Then we use flash memories, which are even more bigger, even more slower, but again, they are far away from the processor. They do not create a hindrance in the overall memory, overall system performance. So overall system performance, whatever fastest memory we use it. We use a SRAM and very near to the control. So this is just to give you a relative idea that how different kind of memories are used at different places for different purposes in a computer system and in a memory hierarchy. So going down, uh, so as I said, we have different kinds of memories, and I'm just trying to classify them. The volatile memories. By volatile, what we mean here is the power goes off, we lose the data. So within volatile, we have random access memory, which we will be talking about SRAM today. And then we have non-random access memories, where when we say non-random access means you can't simply give an address and access any particular location. It works in its own order, like a FIFO, first in, first out, LIFO, last in, first out. While SRAM, the advantage of random access memory is that any location can be accessed. Whatever word you want to access, you can access. User can access any location. Then we have non-volatile read-write memories. Non-volatile, when we say, what it means is that data remains there even if the power goes off. So that's the advantage of non-volatile memories. And then we have read-only memories where you can't write, you can only read, and data stays there. So kind of the applications, no, mostly application of ROM is that boot code is programmed there once for all, and it stays there. You just read it whenever there is a power up needed. So this is a broad level classification of memories, and during this presentation we will be talking about SRAM mostly. So as I already mentioned, the uses of the memories, where to use what kind of memory, depends upon the application, depends upon the cost constraints, performance constraints, PPA constraints, and that's how the memories are used. So if we just talk about DRAM and SRAM. So normally when you use when you need lots of memory and you need cheap but you can live with some slowness, then DRAM is used. And SRAM mostly would be used when we need it access to be very fast. Okay? So these are kind of differentiation between how an SRAM and a DRAM is typically used. SRAM uses, I will not go about each and every bullet here, but yes, we know that we use SRAMs in computers, in communication devices, automotive industry, in all the gadgets, all the modern appliances. We use SRAM, and overall, we can say whenever we need high speed, reliable, low power memory uses, and density is not our top of the priority, then we use SRAM. So this was a typical memory input output pins. So we have addresses to select that, what part of the memory, which word in the memory we want to read or we want to write. Then we have write enable which helps us to decide that whether it's a read operation or a write operation. Chip select, which decides whether at all we need to use that memory as of now or not, because there could be several memories. So which memory needs to be read? That is a lot of times controlled using chip select. Then output enable, because there are several memories right, at a time writing on the bus. So output enable is used to control that which particular memory will put output its output on the shared bus. And then we have a data and output pins. Data pin basically which carries the data which needs to be written inside the memory, and output queue, which is the whatever was written inside the memory. Once you read that data, it comes on the output queue bus of the memory. Okay, so going ahead, this is the logic diagram. Considering memory as a black box, let's say as a box, you can see that all the address, chip select, write enable pins would be there. So here it is typically same, more or less same as what I said before. Just I want to stress upon this last line where I have used a condition which is kind of forbidden, because if you have both write enable on and chip select is on and output enable is on, uh, this is, let's say, not allowed condition, result is unknown. But if a user gives that condition, that what will happen is modeled in the memory verilog models. So a user will typically first make the design based on the model, and that's how they will know what kind of combinations on these pins are allowed, what is not allowed. And then once their design is final, they will replace the memory model with the real memory. So now going ahead with the architecture part. So here I have shown a very, very basic array architecture of the memory. So let's say we have to start with, let's say just we have four words, okay, and each word has 4 bits. So I need to store this 1010 on the topmost word, then 1111, then 0001, and then 1001. So I've just tried to show here, the hierarchy within the word, how these different bits are stored. When I say 4 bits, each word is comprising of 4 bits, 4 sets of data in the form of 0 or 1, right? So I have 4 words here in this picture, and each word is having 4 bits, right? And to select one out of these words, I will need 2 address lines, which I will put a decoder or something in place, which will tell me that, okay, if my address line has 00, then select the 0th row. If my address line has 11, select the last row or the third row. For example, 0123 is the row number, right? So this is a very, very basic array architecture that anyone can imagine when we talk about memory, that there will be words and words will be stacked over each other, and each word will have its own bits, right? But this kind of basic architecture starts to, create some problems, which we will talk about later. So first, we will just see that, if this is the array, okay, this is the array we were talking about, and then we have row decoder, which I said we will need 2 address lines to decide which out of these 4 locations I want to address, and each of these word will have its own bits, right? And then once we read from the memory, there will be sense amplifiers which will read what was there. Suppose I choose that this particular location, whatever was there will be read, and then I will get data on the I will get whatever is written inside, I will get on the queue. If I have to write, I will put some data here, it will go inside and it will write in this location, whatever I have chosen based on the decoding based on the address, right? So this is a very basic imagination or basic thing which you can think of when you think of a memory. So now if I say that, okay, instead of 4, I had, let's say, 512 words. So we would say, okay, these 512 words can be put on top of one another, right? Uh, but practically, it becomes problem. We will talk about that. So let's imagine we have from 0th word, on the top to all the 511th word, all stacked one over the other. And there is a 8-bit in each word, and we are going to read these 8 bits from any word, from one word at a time, or write these 8 bits on any one particular word, depending upon what is the address which has arrived. So if we have 512 words, we take log of this 512, and we need 9 address lines to select which out of these 512 words needs to be selected, right? So, but there is a problem associated, because you imagine that this memory starts to become so tall. Okay, so I have just taken a small example of 512 words. There could be 16k words, 16384 words. So you can imagine that the memory becomes taller and taller and taller in terms of dimensions. Okay, so if we for a moment look back at our first picture, okay, you will see here, right, that if the memory is kind of rectangular and takes one full area, one full end of the processor, our chip, it becomes very difficult to route such a memory to put other important blocks in the same area. So it starts to pose difficulties when it comes to memory uses on the SoC. And it also starts to become very high power consuming and low speed, because of the arrangement of these words, which are stacked one above the other. So in general, what happens is that we don't stack words one above the other like this, right? So this is not the way it is done practically. So practically, what is done is, I will show you here. Okay. So, practically, what I was saying, that practically what we do is we use a certain number of words in each row. So I have taken an example here, like for example, we are putting 4 words in each row. Okay. So in the previous slide, we said, right, 512 words stacked one above the other. But what we will do actually is that we will put 4 words in each row. So this now number of rows here becomes 128. Okay. So total number of bits stored was supposed to be 512 into 8, because there were 512 words of each of 8 bits. But what we converted it into is 128 rows, and each row has 8 words, and every word has 4 bits, or sorry, 4 words, and every word has 8 bits. So it becomes 32 bits in one row. So we have 128 rows, and each row has 32 bits. So total storage capacity remains the same, but now the memory is squarish, okay, easy to work with in a SoC. So as I explained, number of rows becomes 512 divided by m, which is 4 in this case, and number of columns becomes 4 into bits of each word, which is 8 in this case, right? So this is how practically the memory would be organized. Now, since we have 128 rows, so instead of 9, we will need 7 address lines here to decode which out of these rows needs to be selected. And then, since we have multiplexed here, we have put 4 words. Now we need something to select which out of these 4 words needs to come out of the memory. So for that, we will use out of the 9 address lines, we have used 7 here, we will use 2 here. And with the help of these 2 address lines, we will select 1 out of 4 words here using some circuitry here, which is called column mux. And then we will get our desired word out of the memory, whether we are reading or whether we are writing. We will do the same thing. So we will take questions later. I hope this part is clear so far. Okay, so as I said, the advantage is squarish dimensions, good for SoC implementation, and there is an optimization of RC load on critical signals. So we will talk about it further, what I mean when I talk about RC load. So this is just to show what I was saying before. We have 4 words, okay, And so we were supposed to have 8 bits. So we have bit 0, bit 1, let's say till bit 7. And this bit 0, for example, now this has not a single bit 0, but it has 4 bit 0. Bit 0 of word 1, bit 0 of word 2, bit 0 of word 3, and bit 0 of word 4. So if there are m words, m minus 1, which is bit 0 of word 3. So bit 0 of word, I should have written actually word 0, bit 0 of word 0, bit 0 of word 1, bit 0 of word 2, and bit 0 of word 3. So that's how we will have 4 words here. Okay, so I hope this part is clear. We'll go to the next slide. Okay, so now I can again go back to the, or maybe this slide also I will cover in the same way. So as I was saying, this is the whole memory array which we talked about just now. Then this is the row decoder which will select that which location, which row needs to be accessed. Here we will have some control circuitry which will decide, which will decode the addresses, send them above, and then column decoder which will send decode the column addresses and send them this side to select that which word needs to go out, right? And so what I have shown here is the brown color is the read path. Okay, so you give address, you give clock, chip select, and then your address gets decoded. You select a row, select a word line, you select a bit or the word which needs to be accessed, and the corresponding data comes out with the help of these column selectors here in this part of the memory. For write, again, you select the address, you decide which particular row and which particular column needs to be written, and whatever data needs to be written goes from this side, from the lower part of the memory, let's say, and through the column selectors here, it goes to the right column wherever it needs to be written. Okay, so this is how on the overall SRAM architecture, or in general any memory architecture, is envisaged or it's put into place. Okay, okay, so I hope this much is clear. Okay, so now we will talk about a typical read-write cycle, signal flow. Okay, so we select the memory using the clock or the chip select depending upon the overall SOC implementation. As I said, we will be having addresses. Okay, and address is will decide which row or which column needs to be read or written. So corresponding to that particular address, there will be a word line which will be selected. Mm, and corresponding to that particular bit which is selected, the the bit line of that bit. So I'll just for a moment go back to my previous slide, okay, and I will emphasize one more thing here. So as I said, here once we select the word line, this is the word line which goes and selects the bit cell. We will come to the bit cell, what is happening inside the bit cells. But this is the zoomed part of showing that when I show this box here, this is a bit cell where the from where we are reading the data or writing the data. Okay, and this is the actually the bit cell. Okay, we will go in the details of this bit cell. So if you see all these bit cells here, okay, or here, okay, so on the column side, all these bit cells are sharing one single node which is called the bit line, because this is the bit line which is going to reflect that whatever was stored in the bit cell, this bit line will carry it to the outside world. And similarly, when we have to write, we will be writing on this bit line, and that will get transferred to the bit cell. And which particular bit cell corresponding to which row, okay, then that will be selected to this word line, which will come like this. So this is the word line of the bit cell. This is the bit line of the bit cell. So these two are very, very important long signals, okay, and they decide eventually what is getting written here inside and on which cell it is being written. So this is what is the the kind of signal flow. So once the address comes here, a word line is selected. So I've shown two colors here. I'm trying to show two different word lines. For example, in this cycle, there was this word line being selected, word line 0, for example, and in these two cycles, let's say a word line 3 was getting selected. So whichever word line is getting selected, corresponding to, and whichever bit cell is getting selected, corresponding to that bit cell, corresponding to that column, the bit line or bit line bar, one of these bit lines is going down. And then depending upon, suppose this first cycle was a read cycle, so there was a SAMS enable which was coming, and whatever was there inside the bit cell is coming out at the Q bus. Okay. Now let's say the next cycle was supposed to be a write cycle, and let's say a different word line, a different location was being selected. So a different word line is selected now, and a different set of data has come which we are going to write inside, and corresponding to the address, because the address also could be different here, that's why a separate word line is selected, and maybe a different bit line pair is getting discharged now, and we are trying to write in this bit cell. So we are writing in this particular location now. Suppose in the third cycle we are going to now read this, so again the same word line is getting selected based on the address which we have chosen. Now, instead of write enable, this time sense enable is getting selected, and then we are going to have a dead down the queue corresponding to whatever was written in the previous cycle with the help of this bitline pair. Okay, so coming back, I'm just trying to show you that there could be a separate bitline pair which is getting selected in one cycle. There could be a separate bitline pair which is getting selected in the next cycle, depending upon which particular set of bit cells, which particular word we were, intending to write, and that is decided based on the address coming here, and then the memory internal decoders which are decoding this address and deciding that which particular row and which particular column we are going to read or write. Okay. So, as I mentioned, that these word line and bit line, they play a very important role, right? So we know that they are capacitances because these are the signals which are running all across the memory. These are very important and heavily loaded signals. So to gain on access time, to gain in the frequency of operation, sometimes in fact not sometimes, I should say a lot of times, okay, when the memory size increases, we can't continue to have one single SRAM array. Okay, so we partition that to reduce the load or the run length of the word line or the bit line. So this is a kind of a partitioned array architecture, where again going back to the previous slide, suppose this whole one single chunk, and if I divide it into multiple chunks, so then there will be multiple chunks of memory array which will be selected based on the address, and at a time one of these box or one of these arrays would be writing on the output bus, and again the selection will happen through the address, that which particular box or which particular array block writes on the global data bus or the global queue bus, right? So this is again the representation of partitioning of the SRAM, that when the size gets bigger and bigger, we might have to, within the same memory, we might have to partition the memory in the smaller, you know, block of words and bits. And based on the, so one level of decoding, I already explained that address, there was initially 9 bits of address bus, for example, and then we divided into rows and columns because we interleaved 4 words in a row. So we were having 7 addresses to decode the row and 2 addresses to decode the column. Then if the memory size is becoming too big, there can be one more level of splitting, where the first few bits of the address will help us to decide which particular block, which particular array we are going to select, and then within that array we will decide which row and which column in the same way as I explained before. So then in such a cases there will be multiple row decoders, right? Multiple column decoders, because the arrays are different, right? And whatever part of the circuit can be clubbed together will be clubbed to save on the area. Similarly, we can divide the bit line into 2 parts, word line into 2 parts. These are just the representation of how bit line and word line, divided word line architectures are put in place. So if you are keeping the column side the same, consistent throughout, but you are dividing the memory into two parts, or horizontally, for example. So you are deciding to split only the word line. Then also it is possible we just put between the two blocks, we put some more repeaters, some more buffers, and at a time only half of the word line will be selected. So the load on it will be lesser, and that's how we will gain on the performance. So as I explained, single unpartitioned array can be the choice when it is when we want small capacity memory. But as the capacity increases, we may have to divide word line, bit line, and put in place different kind of architectures, which can be done easily. And but whenever we do this kind of partitioning, there is some cost on area, because the more the partitioning, more the repetition of blocks like row decoder, column decoder, right? Because each partitioned block, each sub block will need its own row decoder, need its own column decoder when the reading and writing is happening. So as we increase the memory size, to gain the performance, we may have to do the partitioning, but it may have some impact on the area. Which and these are the kind of trade-offs which a designer needs to take care of, depending upon the targeted application, depending upon the customer need, that whether we will make one huge memory or we will divide it into subblocks. And then, we saw in the previous slide, that finally all the reading writing is happening through the bit cell. So it is the bit cell which is has a very very significant impact on the PPA, well, not just the timing but also the area. So we will now focus further on the SRAM cell, that how actually this reading and writing is happening through the SRAM cell. So typically, a lot of times, what the most used cell for a one read write port SRAM cell is 6-transistor cell. So we will be talking about that in this presentation. Though there are many variations possible, and there are multi-port SRAMs also, where you have many read and write ports available, right? And the cell area may keep on the number of devices could be more or could be less also. But those are not in the agenda today. We will be just talking about the 6-transistor cell. Once you understand that, I think the other cells, it's very easy to understand. So coming to the typical mostly used 6-transistor SRAM cell. So actually this SRAM cell is a collection of two inverters, back to back inverters. So it's a latch actually. Okay. And this latch is connected to the outside word of the memory through the word line and the bit line. And this the connection through the word line and the bit line, I'll just try to explain here. This was the bit line which was carrying the information outside and carrying the information from outside to inside. This bit line is shared among all all 60 SRAM cell in the column, and similarly all SRAM cell in a row share this word line net. Okay, so these are the two access transistors which decide that whether we are going to impact this internal nodes or not, because it is this A and A bar which represent the stored bit. Okay, and this is the data. This is the main data here, which we are trying to store, we are trying to read, we are trying to write through this SRAM cell. So this SRAM cell, as you can see, is a two back-to-back inverters, and within each inverter, obviously, there will be a PMOS and a NMOS. Mhm. And the you can see here that, for example, this A node, this is driven not just through this pass transistor but also through this inverter. Okay, and similarly, this node here, it is driven not just through this pass transistor but also through this inverter. So I will explain in the next slide the purpose of this. Okay, so the most important thing here is this structure of back-to-back inverters connected to the word line and the bit line through these two pass transistors. And this comprises the 6 transistors, 1, 2, 3, 4 in this inverter, 5, 6 in this inverter. So that's why it is called a 6-transistor SRAM cell. Okay, so if you see here, um, how this data storage works. First, I will try to explain the storage part, not the reading or the writing, just the storing of the information. So when we are not reading or writing from this particular bit cell, these excess transistors are off. Why they are off? Because there is no signal on the word line. It is zero. So this is an NMOS. When you put a zero here, this NMOS is off. This NMOS is off. Now our two inverters are the only, they are left like an island here, right? And suppose there was a zero here and there was a one here. So if A is zero, this A bar is one because they are connected through an inverter. And if this A bar is one here, this A is zero because again there is an inverter here. So this pass transistor is off. This pass transistor is off. So this is just a you can say zoomed version of this INV1. So we have a PMOS, NMOS. This particular transistor is off. You have a zero here. You have a one here. And for this inverter, again you have a one here. This inverter drives a zero here, even though this transistor is off. This pass transistor is off. So basically, this is just to tell you that when this Excel is not being read or not being written, this is how, with the help of these back-to-back inverters, this data is maintained here, provided the supply is there. If the supply is not there, obviously the data will not be maintained. But if the supply is there, the data remains maintained. So this is how a 6-transistor cell maintains its data. It stores the data and retains the data. Now, how this reading operation happens in a SRAM cell? So again, these are the 6 transistors. I have named them M1, M2, M3, M4, M5, and M6 so that when I refer to them, it will be clear to you. Now, how a typical read operation happens is these were the 2 bit lines, right, which were connected to the this 60 cell, and this 60 cell is made on, or let's say selected through this word line. Okay, so this word line is going high. Here I have shown this word line is going high and selects this bit cell. Okay. And now we want to read. What do we want to read? We want to read the information. This A is, let's say, 0. We want to read that this A is 0. We don't know already that it's a 0. We want to read, right? So now when we said these bit lines are initially starting with high, so they are made VDD, they are recharged. Okay, and now what happens is this word line is made on. Okay, so if we talk about this M5, okay, this M5 is perfectly on because it has a VDS, it has a VGS. I'm assuming that everybody is aware of the CMOS, how the CMOS transistor works. All the students here are aware. I'm hoping that. So there is a VDS and there is a VGS. So this NMOS is on. This M6, there is no VDS because this side we had one. So both are one. And this also both are one. So there is no VDS, no VGS. This side is off. Now when we talk about M2 and M3, okay, here you see there is a 1 here, so which goes in here, and this M2, okay. So here its VDS is VDD, but VGS is 0 for M2. Similarly for M3, VDS is VDD, but since it is connected to A, this A here is 0, the VGS is 0. Okay. For M1 and M4, we have VDS as 0, but VGS as VDD. Okay. So this is just to explain you what is happening in this 6 transistors. So since this is an inverter, so obviously there will be at a time either the PMOS is on or the NMOS is on. So this side we had 0, the gate of this inverter is 1. So for this inverter, NMOS is on and PMOS is off, okay, or VGS is not there, you can say. Now, because of this, what happens? When you select the word line, the bit line gets a path to discharge. So this transistor is on, this transistor is on, and this bit line will discharge. This bit line will not discharge because there is a full VDS here. Okay, but so there is no VDS, one, 0 here, 1 and 1, and there is no VGS here, 1 and 1. Okay, so this transistor is not helping, and this bit line does not get to discharge, while this bit line gets to discharge. So with this, what happens is that out of these two bit lines which were connected to this SRAM transistor, 60 SRAM transistor, one of the bit lines discharges, other does not discharge. If there was a 0 this side, if this 0 was this side written here, and this was 1, then this bit line would have been discharging, not this bit line. So this is the difference of, the side which has a 0, that particular side of bit line will discharge, and this is the thing which is detected by our sense amplifiers. I will not go into the detail of sense amplifier design because each of the SRAM block needs a separate lecture on its own to explain how it works. But as of now, I will just say that if B is discharging and B bar is not discharging, let's say my sense amplifier will detect a 0, and on the Q bus you will get a 0 because there was a 0 stored here. If B bar was discharging and B was not discharging, then my sense amplifier would have detected a kind of 1 here, because this side I am having 1 and this side I am having 0. So B bar discharging and my sense amplifier will detect a 1. This is how the read operation works. Now, what can go wrong? Because whatever I explain, it all works fine, then everything is good, nothing can go wrong. But there is something definitely which makes it little tricky. Okay, and what is that? So as we see, when the bit line is discharging, it is discharging through M5 and M1, right? And M1, we said that the gate of this NMOS is 1, and this is 0, and this is also 0. So VDS is here is 0, and the gate is 1. So VGS is there, but VDS was 0. So why this was discharging then? How? Because initially when the bit line starts to discharge, it creates some voltage here, right? This node, this capacitor here will get charged little bit, which will give VDS to this gentleman, this M1 transistor, and that's how it will start discharging, right? So as you can see here, that your line comes, bit line, one of the bit line starts to discharge, and between these A and A bar nodes, right? A bar was supposed to be 1, it remains 1 almost, okay? And 0, does this 0 does not remain a full, flat, complete 0. It gets some charge built up here, okay? And that is necessary. It is necessary for the read operation that there is some charge built up here, something coming here, some voltage coming here, because then only this M1 will get some VDS and it will help in the discharge of the bit line. Now, what if this 0, instead of remaining, let's say, up to 50 millivolts or 100 millivolts, suppose it gets charged so much that this you can see here, this A is connected here. So what if it gets charged so much that it becomes a 1? It is being understood as a 1 by this inverter. So if this inverter starts understanding this A node instead of 0, it starts to understand this as a 1, because suppose we are operating at 1 volt, and this 0 has become now 500 millivolt. This 500 millivolt is good enough to make this M3 on, right? And then the whole mechanism will get spoiled, because we wanted that this bit line should not discharge, only this one should discharge when there is a 0. But if this NMOS becomes on, because this A, raise is rising undesiredly, okay, this much is desired, but if it goes even further above, then my bit bar can start discharging, and then sense amplifier gets confused because now the both bit lines are discharging, right? Either the sense amplifier gets confused, or even the worst case could be that the cell flips, because this 0 is no more a 0. It starts to rise. This inverter sees, oh, my input is rising. So now I have a 1 here. So this A bar goes down. This A bar goes down. Now this is connected here, right? This M2 and M1, they are connected to A bar. So when A bar goes down, they also think that, okay, now we have 1 as an input. Instead of 1, we are having 0 as an input. So they also become 1 at the output. So in the worst case, the cell can actually flip, which is what needs to be avoided by carefully designing of these sizing of these 16 SRAM cell. So yeah, I know for a beginner it could be confusing, but it's not that complicated. These are just two back-to-back inverters, and if one node rises above the threshold limit for the other device, it can be misread as the opposite data, and then the cell can flip within itself. So if I go back to this particular representation, maybe it will be more clear that if this is a 0 and this is a 1, so long it remains 0 and 1, it is fine. But if this 0 is disturbed and this 0 becomes, let's say, half of the VDD, for example, I'm just exaggerating, but if this becomes, it rises so much that it becomes half of the VDD, then this is read as a 1 here. And actually V1 can go down actually instead of up being 1. And once V1 goes down, actually V2 can go up. Okay, right? So if this is what I've tried to show here, that if V1 is this V in rising, okay, so eventually as long as it remains up to this limit, maybe it's fine. But there will be an area, if it rises up to this much, my V2 will also start to rise. V2 will flip, V1 will go down, and the cell can get flipped. So this is what we have to avoid by the careful choice of the dimensions, the sizes of these transistors, so that a read remains a pure read and the internal flipping of the cell does not happen, or it should not happen that bit bar also starts discharging so much that the sense amplifier gets confused, because sense amplifier is designed to read one of these bit lines going low and the other should stay as it is, or maybe up to the tolerance limit of the sense amplifier based on the design of the sense amplifier. So this is what I already explained, that what is the flipping mechanism of the bit cell, and this is what is a very important criteria in the designing, and it is called static noise margin. So it is the maximum value of noise which this cell, okay, so suppose imagine there is a noise coming from somewhere. So as it is already, there was this A node was rising little bit during the read, which is needed. It is needed to rise. Otherwise, read operation cannot happen. So small rise will anyway happen. But over and above that, there can be many sources of noise. So this SNM, this keyword is used as a figure of merit for this SRAM cell. That what is the maximum value of this noise without making the cell flip. So without flipping the cell state, how much noise this cell can tolerate. This is called the static noise margin of the cell, and it is a very important criteria of SRAM cell design. So then, how the writing happens in the SRAM cell. So again, we have these two inverters connected back to back. We have these two excess transistors. We have our bit line and we have our word line. So once the word line comes here, we know that this cell needs to be written. Now, if it is a write operation, we will not depend upon bit line to self discharge. Suppose there was a 0 here, okay, there was a 1 here, and now we want to write. We want to convert this 0 to 1 and this 1 to 0. So what do? We ourselves in the by SRAM design process, okay, depending upon what data needs to be written. So suppose the data which needs to be written is that this 1 needs to be converted to 0. Then this side of bit line will get discharged. Okay? We will discharge based on whatever is the data to be written. We will discharge that corresponding bit line. So if we want to write a 0 this side, we will discharge this bit line. If we want to write a 0 this side, we will discharge this bit line. So now when this bit line is connected to this circuit, and this circuit is called a right driver circuit. So this right driver circuit, what it does is it discharges the bit line. When it discharges the bit line, and since the access transistor is also on, this side of the bit cell also discharges. So there was a 1 stored here, but it gets a path to discharge. So this current is now flowing like this to the ground, and this node gets discharged. When this node starts to discharge, as you can see here, A bar starts to go down. When A bar starts to go down, it is coming here, and this inverter starts to understand that okay, I'm getting now 0 as an input. So if I'm getting 0 as an input, this PMOS will get on, and this PMOS will get on, and it starts to put a 1 here on this node. So A, which was actually 0, starts to become 1 when A bar goes down. So the trigger point comes from the A bar, and A bar is discharging because we are making this bit line getting discharged because of the data we have chosen to return. So this A bar goes down, this A goes up, and the cell gets flipped. Right? So this is how the writing mechanism happens. Now, what can go wrong during the write? Okay, because the whole mechanism is depending upon this access transistor being on and helping to discharge this internal node, because if only the bit line gets discharged but it is not connected to inside of the bit cell, then there is no point. Cell will not be written. You can do whatever with the bit line, but the cell will be affected only if bit line and the cell are connected with each other through this access transistor, pass transistor. Right? Now, one of the reasons why write can go wrong is we we are still in the writing process. A bar was going down, but the word line gets off. Word line, this pass transistor goes off because the word line goes off. See here, this word line going off. So if this word line going off happens before this internal tripping, suppose the word line was going off here itself, suppose, then this cell will not be written. So these are the things which can be prevented by careful designing of these mechanisms, these circuit, the row decoder circuit, the write driver circuit, because these are the circuits which decide that for how long we are discharging the bit line. Then there is another circuit which is deciding that for how long we are keeping the word line on. And these are the things which are being managed when we are designing the memory, that we have to ensure that bit cell is fully written. 1 has become 0, 0 has become 1 before we make these pass transistors off. Once this has happened, then we know our 60 transistor cell, our these two back-to-back inverters can sustain the data within themselves because these are back-to-back inverters. And we don't need this pass gate, this access transistor to be on after the flipping has happened. But when the flipping is happening, we need these pass transistors to be on. So this is the thing which are again very carefully designed when we are designing a SRAM cell and SRAM circuit, because now this mechanism of word line getting off, this bit line getting discharged is not being controlled by the cell. Cell is controlling the internal nodes. These mechanisms are being controlled to the rest of the circuit of the memory. So that is where the rest of the circuit also becomes very important. Okay, so I think I have explained the transistor in quite a detail now. So just to refresh that what are the design criteria for the memory cell. So cell the stability because it needs to store 0 and 1, and this is 0 and 1 we need to preserve it. During when we are reading, it should remain preserved. When we are not reading a particular cell, it is that particular word line is not on, and the data should remain stored there. And also during power down modes, to save power, there are many power down modes designed in the memories where we do not take away the VDD completely, but we want to lower it. Okay, when the memory is not being used, we want to lower the VDD and save some power, but we want to preserve the data. So our bit cell should be designed in such a way that to some extent we can save power by lowering the VDD and the data still remains there. SNM we already talked about. Write margin, um, basically for how much low I need to take the bit line to actually write my bit cell. Do I really need to make it fully 0, the bit line, then only the bit cell would be written, or I have some margin there? So that is what is called the write margin. Then we have seen that uh, because bit cell is a very important part and it consumes a lot of area. So sometimes we have seen that when the memory is lots of words and bits are to be stored, bit cell area, bit cell can take up to 80% of the total memory area. So one of the key cell design criteria is also the keeping the memory bit cell area as optimized as possible. And we have seen that these word lines and bit line nodes are so important in deciding the performance because it is this bit line which will discharge when we are reading or writing. And it is the word line which will get selected and deselected when we are reading and writing. So the RC load on these nets is very important, and which is the RC load of these nets. Basically, if we go back, the load on the word line and the load on the bit line is hugely dependent upon the sizing which we have done in the bit cell. The sizing of the M5, M6 uh, is great. It's a big contributor to the word line and the bit line load. So that is those are the things which we have to take care when we are talking about the bit cell design. And of course, we need to take care of the bitline leakage also, because we don't want that, as we saw in the read operation, right? We don't want that bit bar when we are reading and we want bit to discharge. We don't want bit bar to discharge. But if there is a lot of leakage in M6, and as we can see in the previous slides, we have seen that every bit line has many, many bit cells connected to it. So there will be, let's say, 1,000 M6 transistors coming from 1,000 cells connected to one bit bar. And if the M6 is a leaky transistor, the bit bar will also start to go down just because of leakage. And again, my sense amplifier will get confused. So these are the things which determine that the cell design. Okay. So now those were the design criterias or which we have to keep in mind. And also, I want to tell you what are the constraints in the sizing. We cannot choose whatever size we want. Okay, there are pros and cons of increasing the access transistor size, increasing the PMOS size, increasing or decreasing the NMOS size. So we will go about them one by one. So if we talk about access transistors, when I say access transistors, I talk about these M5 and M6, which were connected to word line and bit line. Okay. So basically this M5 and this M6, these are the access transistors. So if I talk about M5 and M6, okay, their width and length of the sizing of these transistors determine the read current, right? The read timing, because if I have a good W by L ratio here, my read current would be, if I talk about read, for example, this I cell, okay, this I cell would be better if I have a good W by L here, right? M5. And similarly, when this bit bar is discharging, if I have a good W by here, my read current would be good. So higher W by L means high read current, which means faster read and faster write. But then high W by L means increasing the load on the word line, increasing the load on the bit line, so that in turn slows down the memory. Mhm. Then it also means that internal node, which is a very small node which was charging and discharging to store the data, and this node also capacitance is increasing, so this node also takes now more time to charge and discharge. And the higher this this pass transistor, this access transistor, the higher is the need of this pull down. Okay, because if a current is coming from here, but this transistor cannot take this current down to ground, cannot sink this current, then this charge starts to build up here, right? And then we will have a problem of flipping during the read. We will have a problem of SNM. So the higher, if we choose M5 bigger, we need to choose accordingly M1 also bigger. So there is a ratio which needs to be maintained between M5 and M1, which is called the cell ratio. So we need to, if we make the M5 bigger, we need to make the M1 also bigger. Okay. So and the bigger the M5, it poses some threat to the SNM because it takes more current. It gives more charge to this internal node. which is needed for it. But if it is too high, it might impacts my SNM in the bad way. And of course, the higher the size of any transistor, higher is the area of the cell. So you see, we want to keep it bigger because we want to read and write faster. But if we put it anything, we can't put just whatever we want. Right? There are many cons of putting it bigger. The pull-up transistors, uh, they are there just to hold the data. They are right. So we would want to make them low as possible, because they impact the area. So the smaller the better, right? And if they are small, they are good for cell stability. They improve the SNE. But if they are too small, they impact the write operation. So if we see this write operation here, when my one was going zero, okay, this one going zero, I want this zero to become one. Now, who was helping this zero to become one? This PMOS. If this is too weak, too weak, then this doesn't provide any help when I'm trying to make this zero to one. So my write could become slower. So it badly impacts my write margin, right? Slows down the write operation. Then coming to pull down, again, we want minimum because it is good for area. But we can't put minimum because we need good SNM, we want good read curve. So we have to uh, uh, put some decent size which is corresponding to the fast transistor size and provides a good SNM, provides a good cell ratio, at the same time does not impact the area too much. So that's again we have to decide between the pros and the cons of keeping the sizing of the pull down accordingly, because each of these cell, we have to remember that each this bit cell here we are seeing it one time, but it will be repeated in the array if we talk about the whole array. Okay, so if you see how many times this is 64 cross 128, right? So this is 8k, and let's say how many, these are 8 such blocks, so 64k memory, right? This is 64k as memory. So 64k means 64 into 1024. So these many times these 6 transistors are going to be repeated in the memory. So that's why their sizing, their area is very important, and very carefully we have to design keeping all these constraints in mind. So a typical read cycle, I have already covered it, but just to summarize that memory is selected either with chip select or with clock. The correct address is provided, the output enable is made on so that the memory reads and the data and puts it on the queues bus. Okay. And if there is a shared data bus where some other memories are also sharing the same queue bus, then those needs to be put on the tri-state. They should not be putting the data on the same queue bus at the same time. And then the system will wait for the whatever is the memory specification provided in the data sheet as per the need of the customer, and the system will wait for that much time, and the output will come out after reading from the corresponding bit cell, and that corresponding bit cell is chosen based on the address given. And then, as I said, memory internal clocking, memory reset mechanism, all that will ensure that all the critical nodes, for example bit line, needs to be again taken back to one before a new cycle starts. Okay, because this time we may be reading another bit cell, right? So, and that another bit cell could be using the same bit line because the bit line is shared across the whole column of the memory. We have seen it, right? So once we have read, we need to make sure that that bit line is precharged again, right? Before the next operation begins. So all that reset mechanism, recovery mechanism, taking back the nodes to their default state is taken care by memory other blocks, which we have not talked about here. Control block, row decoders, muxes, precharge circuitry, write driver circuitry. These are many components which needs to be carefully designed. Then a write cycle. Again, we enable the write cycle either using write enable clock depending upon the application. Select the memory, put correct address on the address bus, whichever bit cell needs to be written, whichever word needs to be written corresponding to that. And this data goes inside system waits. minimum time for data to be written. Now, what that time, how that time user will know? User will know through the memory data sheet, which is provided to the user. That once you do the write operation, once you provide the clock, how much time after that you need to wait to be sure that the data is written. Or sometimes with respect to address, this time is given that once you stabilize the address, how much time you have to wait before being sure that the data is written. And then you can start the new operation. Suppose you want to write and then you want to read that data. So how much time after that you can do? And again, the internal clocking and reset mechanism needs to ensure that all the default signals, all the reset mechanisms are taking place, the bit lines are precharged, the bit lines are off, and everything is ready for the new cycle. Okay, so as I said, other than the bit cell, we have covered only bit cell uh, to a good extent in this presentation. But there are many other important periphery blocks, control logic, decoders, muxes, precharge circuits, write drivers, sense amplifiers, and IO circuits, which contribute in the overall memory functioning. Bit cell is the most important, yes, but the others are needed to reach to the bit cell, to write into the bit cell, and to read the data from the bit cell. There are many other important periphery blocks. So that was all from my side for today. Uh, I I hope I have been able to give you a top level idea on memory architecture and particularly the memory bit cell, the design criteria and the design constraints which we have for the six-transistor SRAM cell. Thank you, and that's all for today.
Thank
Okay.
you, ma'am.
Uh,
Thank you for the presentation. Students have actually asked many questions. They are posted in the questions tab. Do you want me to go through it one by one, or and you can answer it, or would you like to just go ahead and take it over?
okay, I will try to read it. Okay,
Yeah.
and if
If you
I'm
go to the questions tab, you'll be able to see the all the unanswered questions. There are 10.
yeah, okay. So this was
Yeah.
about using the pointer. Yeah, I I
Yeah.
realized that my pointer was not visible, so I think afterwards it was okay. Data goes out through bitline or BL or BL bar. Yeah, so as I said, data would be going out. Data, when you say, when we are reading in the memory, depending upon we are reading a 0 or a reading a 1, either the bitline would be discharging or the bitline bar would be discharging, right? So if I go back, maybe I know how to, okay, I'll go back to the presentation. Okay. So as I said, yeah, reading, right? So if this side we have a 0, bitline will discharge. If this side we have a 0, bitline bar will discharge. And my sense amplifier would know that if bit is discharging, suppose it is designed like this, that if bit is discharging, it throws out a 0 here. But if bit bar is discharging, it throws out a 1. So effectively, you have read either a 0 or a 1, depending upon this side you had a 0 or this side you had a 0, right? So it could be anything, either the bit line or the bit line bar, whichever side is having a 0, that side would discharge, and sense amplifier is designed to detect that accordingly. I hope it answers. What is the typical voltage difference in between bit line and bit line bar for lower nodes? Let's say less than 16 nanometer. Yeah, so it depends upon how the sense amplifier has been designed. So if the sense amplifier has been designed to read a 20 millivolt difference, for example, then a good designer, okay, would try to make sure that sense amplifier is made on once the 20 millivolt difference has been reached, and a good reset mechanism will be designed so that you do not discharge the bit line unnecessarily for long, because my sense amplifier, suppose it can read 20 millivolts. Now if I'm still taking the bit line to 200 millivolts, I'm kind of wasting that charge, because I'm discharging it unnecessarily to 200 millivolts, and then I will have to charge it back for the to be ready for the next cycle, right? So how much difference will be depending upon how what is the sense amplifier design. Okay. It could be designed for 20 millivolts or to read 10 millivolts difference, depending upon the sizing which has been chosen. depending upon the criteria which was there in the architectures or designer's mind in terms of designing the sense amplifier. Okay. So what is the difference between high density and high speed? Okay. So high density, when we say density, we talk about area. Okay. So as we have seen, this is the bit cell which will be replicated, let's say 16,000 or 32,000 times or whatever time, number of times, right? So each bit cell contributes to the area because this is the most repeated structure in the memory. We what we mean is how low is the area. So in the same area, how much information is being stored in the given area. That tells that whether it is high density or not. And when we say high speed means how much frequency user can get. So if, as I told you, nowadays in the lowest nodes, we people are achieving up to 4 gigahertz, 4.5 gigahertz speed from the memory. So it's after one cycle, and at then next cycle, what is the minimum gap you can keep? So let's say you can keep 50 picoseconds. It means you can operate at 4 gigahertz. So this is what we mean by high speed. What is the PVT condition to get worst case SNM? So worst case SNM, nowadays things have become so tricky that probably one PVT condition will not be the worst case. Depending upon the node, temperature sometimes poses a challenge. Okay, so a lot of times I have seen we have to simulate in both the temperatures for a given process and voltage. But if you, as we have seen in the read, na, so the slower uh, the the worst is the ratio between these two. And this PMOS, okay, so if we are talking about worst SNM, okay, this PMOS becoming stronger will make the SNM bad, right? This again, these two are both are NMOS. So if one becomes slow, other also becomes slow. So that is something depending upon the technology and depending upon the sizing which has been chosen. Okay, we have to see. But as far as this PMOS is concerned, I can say that this PMOS becoming stronger makes the SNM poorer, because when this zero starts to get become one, if this PMOS is stronger, it reads it as a one. Okay, so higher voltage if you have, okay, this PMOS will be more stronger. Okay, so that would make the SNM bad, right? But other parameters, uh, nowadays sub-threshold nodes are posing different kind of challenges. So it's hard to say one particular PVT. Sometimes there are several PVTs where SNM needs to be verified. Okay. Is how Ratmanin is related to term, because it is unit we have measured in picosecond or maybe in microsecond. Right margin, normally we say about how much the bit line needs to be taken near to zero. So if I have to keep make it completely zero, or let's say I'm doing a 1 volt operation, can I just take it down up to, let's say, 300 millivolts, 200 millivolts, 100 millivolts, and still I can write, let's say, then I would say I have a write margin of 100 millivolts, right? And as far as timing is concerned, sometimes in when we are between designers, okay, terminology becomes our day-to-day language becomes our terminology. So sometimes right margin, when we say, we talk about this margin, like this one, the word line going off. Okay, so my internal nodes were flipped. So how much margin I was having in terms of timing, when it comes to picosecond, we start to talk about this time as the right margin time, that this bit line and this internal nodes getting flipped and word line going off. So do I have a margin here or not? Is my word line getting off just when the bit line, just when the internal node was flipping? If that is the case, then my margin is bad. If I have this kind of the example waveform which I have shown, here the margin is good. Your internal node is flipping, and after some considerable time the word line is going off. So this is good right margin. when it comes to time wise right margin. But literal definition of right margin is more to do with how much bitline voltage needs to go down to make the write happen. But in practical terms, when we are within the teams, we start talking about right margin in terms of timing in this way. I hope I was able to clarify. In most of the papers say 60 SM is not the stable for read and write operation. Many other circuits are designed to lower nodes, which type of use based. In my experience, even till 3 nanometer, okay, the XRAM cell being used is 60. Okay, when we talk about 70, 80, those SRAM cells are used when we want to increase the number of ports. Okay, when I say increase the number of ports, imagine you wanted, you know, let's say I'll go to the logic diagram of the memory. Okay, so suppose here I have one address bus, right? Suppose, or maybe this one. Okay, suppose I wanted, uh, I'm writing data from here and I'm reading from here. Suppose I wanted this side also. Okay, I'm just using this as a picture as to help me explain you. So suppose I wanted to have another port, another way of entering this array, another way of reading and writing into this array from another direction, let's say. So some applications want to use it, right? By the time they are writing, suppose they are writing on one location here, and there is another port which is reading another location. Okay, or let's say you are reading one location from this side and you are reading another location from another port here. Okay, so that port, the Q and D, will be this side, for example. Okay, just to give you a more idea on what I mean by port. So let's say there is one column X here, probably there will be one here, and you are doing some reading and writing also from this side of the memory. So when you have multiple ports, then you will need a SRAM cell which will have more transistors. So this 60 will become 80. There will be, let's say, one more set of pass transistors here, which are connected to another word line, and that another word line is being controlled by another port having another set of address lines. So it is possible that one port is reading from one location, another port is reading from another location, and that's how you increase the overall throughput of the memory. So some applications use this, and then only in those cases um, we need more transistors, 8 transistors, 10 transistors. Otherwise, typically I've used in most of the conventional SRAMs, the 6 transistor being used. Then there are DRAMs which are based on the single transistor, right? That's a different operation altogether. But when we talk about SRAMs, uh, it is all 6 transistor, right? Okay, so I think most of the questions are covered, Anush. Yeah, for learning memory further, yes, this is one thing which I would like to take up. See, there is a lot of data available on the internet anyway, but recently I've seen that from one of my colleagues at ST, in fact, who is also a professor in Triple IT Delhi. I have seen very good presentations on all the topics of memory available. And of course, I think others will comment further from Chipet's side if there is anything more available on the memory side, how people can uh, read further. But there's lots of data available. Um, you you can go through yourself, or maybe I don't know if others would like to add here if there is
Yeah.
something.
Thank you, ma'am.
Yeah.
Thank you for this session. We had a good response from the students as well, and they were engaged throughout the session. They posted the questions, and you have answered them perfectly. So from our side, I'll be posting few resources for the students which they can access. Along with that, if they have any feedbacks or any questions separately from us, uh, they can either send it to my email ID, or we have our own contact info which I've shared in the chat. So, guys, I would like to convey that all the webinars we do every month are recorded only, and we would be soon uploading this webinar to a YouTube link, which I've already shared in the chats. You can access it there. With respect to the enquiries regarding the course, you can drop an email either to me at the email I've provided down below, or you can connect in the number provided, where you can get all information regarding the courses we are currently providing and the courses we are going to do in future also. So you can connect with the expert and get a clarity on that. And thank you very much, Nutan ma'am, for connecting all the way from a different country and taking your time and joining in the correct time and making sure the entire thing went very smoothly. From the starting of the session till end, I was connected throughout, and I listened to everything you were saying. And I would like to say there were very few lags and mistakes from your end, so it'll be a easier job for our editor also to edit it and post it on YouTube. So thank you very much,
Thank you.
and I hope you have a nice day. And thank you everyone for joining. And we'll be doing webinars next month. You can all stay connected to our social media pages, which I've shared over the chat. Thank you, and thank you, ma'am. We'll close this session.
Thank you. Thank you, Adarsh. Thank you for everyone who
Okay, ma'am.
joined.
Bye.
Bye.